let's see. So I actually went to our workshop website and tried to grab what is the actual goal of this workshop, and I tried to paraphrase it here. And it's how can we use machine learning to understand the physics of galaxy evolution? And we have seen over the past few days, there are obviously many different ways of how machine learning can help us. And I just listed a few examples here, like so we can use it for automation purposes. We can use it for deep Bayesian inference, like we just heard this morning. Another good application is to use it as emulators for much more costlier models. And this helps, for instance, if you want to generate mock catalogs and things like that. Now, in each of these cases, training data is essential. And for me, as a simulator, of course, the training data are cosmological simulations. So as you are probably very familiar with, there are two main kinds of cosmological galaxy simulations, so-called zoom-in simulations and large volume simulations. And there is an inherent trade-off between the two. Zoom-in simulations focus all the computational effort on a very small volume, often a single galaxy or a galaxy group. And so here we get very high resolution, and we can probe and model the astrophysics much more accurately, perhaps. While on the other hand, large volume simulations give us both the statistics and also the larger scale environment. All right. So one way to maybe describe this trade-off between sample size or volume and resolution is via the dynamic range. So we just divide the effective box size of the simulation, and this you will have to define in a certain way for zoom-ins by the effective spatial resolution. And again, here you can have different ways of how you define that. And I show this here. Sorry, now I have to use this plot here at this point. Okay, so here's the effective box size. Here's the spatial resolution. And for a bunch of more recent simulations, state-of-the-art simulations in many cases, and you can see that the dynamic range is maybe a few times 10 to the 5. So dynamic range are these diagonal lines here. So Firebox, which is the simulation that I'm going to talk about for the next few minutes, fits into a unique space here in this plane, and it sits up here. So you can see it has a spatial resolution that is almost as good as the best zoom-ins, not quite, right? It's a bit worse than the best zoom-ins, but it sits there, and it has, and also it captures a relatively small volume. So you can see it's either worse than zoom-ins and worse than cosmological volume simulations, or you can phrase it the other way around, so depending on your point of view. Okay, so so what is Firebox? Well, it is a 22 megaparsec cubed volume, cosmological volume simulation with 1 billion gas particles with Planck 15 cosmology. And it's in particular the first cosmological volume simulation from the FIRE project, that uses fire physics. So compared with previous large volume simulations, it has higher resolution and more realistic ISM physics. The cooling is down to 10K, for instance. The star formation only takes place in very dense gas, so 300 atoms per cubic centimeter here. The gas has also to be self-gravitating, and it happens with 100% efficiency per free fall time. So there's no, coded. So we don't lower the efficiency there. The actual good efficiency that you get out if you measure how efficient star formation is of course much lower because of feedback. So here we use the Fire2 feedback, includes mass, momentum, energy from supernova, stellar winds, and other effects. What we do not include here is AGN feedback. Okay, so that's something that you have to keep in mind when you look at the results of the simulation. Okay. So what can Firebox do? Well, as I said, it has this very high spatial resolution, and this helps with resolving the multi-phase structure of the interstellar medium in galaxies. Here's an example of a Milky Way analog galaxy that's part of this cosmological volume. I show it in optical colors here. Then this is a face-on view of the gas distribution of the 3 different gas components, H1, ionized gas, and molecular gas. And here you see it edge-on. And you can see, for instance, very clearly that this H2 disk is very, very thin. So this has a scale height of about 100 parsecs or so. Okay. So if I want to look at some more, let's say, the quantitative tests, we looked at the content, at the gas content of galaxies, say the atomic hydrogen. That's important for the remainder of the talk. And this looks kind of reasonable compared with observations. We also look at the molecular hydrogen content, looks also very good. And if you're interested in these kind of things, what we predict is that essentially both the H1 and the H2 sequences are broken parallels. So they are parallel here at the massive end, and then they continue to be another parallel at the low mass end. Yeah. Yeah. So this is actually all galaxies here, all centrals, I think. Yeah. But in some sense, it's the same because we don't really have very many quenched galaxies in there. So almost all the galaxies. Almost. I mean, there's some quenched galaxies, but these are mostly with environmental processes. But yeah, for the centrals, they're mostly, the quenched fraction is relatively low.
Since I just hit enter. For the molecular hydrogen, do you assume a temperature profile, or do you just take the cold one that's involved with stars?
So the molecular hydrogen is not modeled. I mean, it's modeled in the simulation, but in a really as a crude way, and that's what we do here. That's really just the Krumholtz model. So for the situation equilibrium, yeah. So essentially just uses the gas metallicity and the optical depth.
And for the H1 and the cell shielding, I mean, is doing through radiative transfer or
no? It's also an equilibrium model. That's so yeah. So this can be in principle, you can take a simulation snapshot and you can do your own radiative transfer analysis if you want. Okay, so this is the cosmic evolution of atomic hydrogen, and it also looks fairly good compared with observations. And then we have this, which doesn't look very good. I mean, it looks okay, but it's not nowhere near as good as we would like. This is the stellar mass function shown either as a differential stellar mass function. Oops, the wrong button, or the cumulative stellar mass function. And we have, I think, good agreement at very high redshift, let's say 6 and higher. Then at this intermediate redshift, things get a bit strange. We're a little bit too high. Our stellar masses are too high. And then at low redshift, at redshift 0, we are kind of almost okay, but only if you compare to this stellar mass function here, which is the dot dashed curve. So Firebox is these, these circles here. So we are a little bit high here, which turns out to be a resolution effect. So the fire physics is not entirely converged at this resolution of Firebox. And we also, and this is seen more clearly if you look at the cumulative stellar mass function, we also overestimate the stellar mass function at the massive end as well. And but this you can understand as a lack of AGN feedback. Okay. So all right. So now I want to switch gears, and I want to talk about atomic hydrogen. And how we can model this with deep learning. So the goal is to predict the distribution of baryons, right, from dark matter. And why would you want to do that? Well, because of course, running hydro simulations like Firebox is very expensive. Running dark matter only simulations is comparably cheap. And this, of course, has lots of different applications. As I mentioned earlier, we can use it for mock maps. We can use it for Bayesian inference, for instance. And of course, we can do this for many different baryonic fields. Here, I'm going to focus on H1, but I also want to point out that there is that we are not the first ones. There are many other people who, many other research groups who have been working on modeling baryonic fields from the dark matter. And I just list the ones that that I know of right now. But you know, I might be missing some. And what makes our approach so special is perhaps that we have a much higher spatial resolutions than what has been done before. Okay, so let me guide you through that a bit. So the approach that we have been developing in Zurich, and this is work done mostly by my PhD student Mauro Bernardini, here shown, is this EMBER, which stands for the slightly tortured emulating a baryonic enrichment network. And the idea is that we want to sample baryonic maps, H1 maps in our case, from a given dark matter map. So we don't want to just to predict the average H1 distribution, but we really want to generate the full distribution. Okay. And the approach is a deep CNN with a GAN, so it's coupled together. So we have essentially a generator, generator component, which is the CNN. It's actually like a UNet, and then we have a discriminator. And it's trained on Firebox and on a couple of zoom-ins that include much more massive halos, because given the size of Firebox, we don't have too many massive halos in it. But it's done with exactly the same physics, with the Fire 2 physics. So the basic idea is as follows. During the training, the neural network learns how to map from the dark matter field, here shown a high resolution, to the gas field, also shown. We do this on the map level, so on a 2D level. Okay, so we slice everything. So we don't. This is not a 3D approach. There are other groups out there who have tried to do this in 3D. And then we also allow other training where we first downsample the dark matter, maybe here to, let's say, medium resolution or low resolution, and then still map it to the high resolution gas. And that's very important because this allows us to upscale. So we can then, for instance, take a large dark matter box at this resolution down here, and then apply the neural network to paint the atomic hydrogen on it everywhere. So how well does it work? Let me give you an example here. So here we have the dark matter shown here. This from the simulation. This is the atomic hydrogen from the simulation, and these are just different zoom levels. Okay, I just zoom in on one halo here in particular. And if you look for like a more simple approach, that would be just a deterministic pure UNet that was like state of the art maybe a few years ago. And you can see it does quite well on large scales, but once you zoom into smaller scales, you get this very smooth kind of prediction, because it makes essentially kind of an average prediction. It doesn't really sample from the distribution. And this is what EMBER predicts for different input noise. Okay, and you can see that so depending on what you put in as input noise, you get a different sample out. Okay, for the same dark matter field, you get a different H1 map out. But I mean, all these look very similar to this. Okay. If you want to be a bit more quantitative, we of course look at things like the power spectrum, or the bispectrum, or the column dense distribution function, and we typically find agreement of order 10 to 20% down to galactic scales. And what we can also do is we can also just project, let's say, the H1 mass within the virial radius. So we can, of course, so this is a completely halo-free approach, but of course we can find halos from the dark matter and then say, okay, how much H1 is in those halos, and we can do this both for the simulation and for our emulator, and you see we find very good agreement overall. So distribution is reproduced very well. Okay, so let me just finish with some outlook. So this is EMBER, let's say 1.0. The next version of EMBER that is currently under development will features a slightly different architecture that is a bit slimmer and therefore fast to train. it will also allow a multi-field output. So at the moment, the network only gives you one field out, let's say atomic hydrogen, but it's, and so of course you can train it for different fields, but the important thing is that you want all these fields to be correlated correctly. So if, let's say, there's a lot of H1 in a region, you want the temperature there to be low, for instance, right? And so you want your network to know that. So that will be part of Ember 2.0. And also, Ember 2.0 will allow that we train on as many redshifts as we like, and then we can interpolate also to any redshift for which we want to make a prediction. And then for Firebox, the paper is out on the archive. You can read it. There will be data products coming out, hopefully in the fall, which will include, let's say, Halo catalogs and Galaxy catalogs and SCD data cubes. And so if any questions, just contact me or talk to me. I'm here until Friday. Okay, thank you very much.
Thank you for the talk. So because of the time, maybe one quick question while Megan can set up your, yeah.
I'm wondering, so the training was done with one ultraviolet background model that you have in Firebox. So if you start to alter that UVB model, the prediction will be different. Mm-hmm. So is that something you're planning to do, or that you've messed around with? Like the UVB will alter the brightness, especially at the small scale H1. Yeah, so the current predictions are fixed to one specific physical model, right? It's the Fire 2 model and the UV background. I mean, rerunning Firebox, that's it's the curse of cosmological galaxy formation simulations. You don't need to rerun it. You can just rescale the UVB. Yeah, so you could do that. So that you can do, and you can then just recalculate the H1 content. So that's so if you're okay with that, then yeah, absolutely. That can be done. I think that would be important because that'll alter the H1 distribution for sure.
All right, thank you. Let's thank Rob again. Thank you very much. So our second talk is by Megan Tillman. She's going to tell us about AGN effects on Lyman alpha forest.
Today, I'm going to talk about AGN feedback effects on the low redshift Lyman alpha forest, so kind of a 180. Now we're only focusing on AGN feedback. So just as a little, overview, what the Lyman alpha forest is for people who don't work with it every day. So we got this nice movie that if you haven't seen, you're seeing it now, and it's amazing if it'll play. So on the left there, you have your source, which is going to be like a quasar in a distant galaxy, and you can see your sight line as you're traveling through the universe. As you travel through this gas clouds that you travel through will absorb some of this light, and that appears as absorption lines in the spectra, and that populates your Lyman alpha forest. So this series of absorption lines allow us to observe something that would probably be otherwise invisible to us because this gas is so dim. So it is a very useful tool that we need to be using more, and we need more telescopes for it. Because at the low redshift, we see a disconnect between a lot of hydrodynamic simulations and what is observed. So these pink data points are what is observed. And you can see in this Kohlmeier study was one of the first to point out, there is a huge offset from a lot of simulations or those the UVB model at that time from what is actually observed, and you needed to strengthen that UVB model by 5 times to actually match what is observed better. So we have stronger UVB models now, yes, but we don't have 5 times stronger, and this may change, but something else that has been shown is that AGN feedback can have an effect on the forest. So if we look at illustrious, that's this red dot here, this or red line here, these are the same observational data points. You can see it doesn't really match the data that well. If we look at illustrious T and G, which has the same UVB but a different AGN model, and that's the main difference between the two, it looks dramatically different. It also doesn't match very well, but a lot of sims don't match very well. So clearly the AGN feedback model can have an effect, and it is something that we should be considering. So now let's look at a simulation that matches a little bit better. So the fiducial Simba results match the observations remarkably well, largely because of the slope that it produces in its column density distribution. And well, what can we attribute this to? Potentially AGN feedback. So let's try removing the AGN jet feedback. Simba is one of the only cosmological hydrodynamic sims that includes jet feedback in their model, which is exciting because when you remove the jet feedback, That is a crazy difference. It's reminiscent of what we saw in TNG, but now it's the same simulation, just removing a tiny subgrid model. So AGN jet feedback can have a dramatic effect. And I'm shamelessly plugging my paper here. This should be updated soon. It was accepted yesterday, so it's still not updated. But now let's consider varying the UVB, because you might say, what if we can just lump all this into the UVB? Why do I have to put AGN jet feedback into my simulations? Well, it turns out that the jet feedback actually affects both the slope and the normalization of the column density distribution, whereas the UVB only affects the normalization. So this is important because when we do fits, when we allow the UVB to vary, we find that the fiducial simulation results actually fit better than the no jet simulation results when we allow the UVB to vary with reckless abandon, not limiting it to what UVB models are available. So this is striking. We need to be putting AGN jet feedback in our simulations because, at worst, it might have the same effect as the UVB and you can lump it in there, but it clearly has an effect and you don't know what else it might affect. So this is something that we need to be considering in the future. We need to build more models because currently there really aren't that many to explore. So just to visualize the effect of the jet feedback in Simba, it's quite dramatic. On the right here, you have some temperature projections. On the left, you have column density projections, and this is just a fly through of the box at Z of 0.1. At the top, you have jet feedback. At the bottom, you don't have jet feedback. These results are clearly observable. We should see this in our observations. And if we use the camel simulations, we can actually explore variations in the Simba simulation jet feedback or AGN feedback in feedback models in general. And on the right here, we have the column density distribution for on the top varying the momentum flux and the bottom varying the jet speed. So the jet speed clearly has a much more dramatic effect. That's because the momentum flux only contributes a little bit to setting the jet speed. The jet speed is what allows the jets to get out into the IGM, and that's what affects the forest. So you also see these effects largely at the lowest column densities. They kind of putter out as they get to higher column densities, not able to affect that media as much. And also this noise is because of the box size. But observational data is pretty sparse there, so we don't have to worry about that at the moment. We can also look at stellar feedback effects, which you would think shouldn't show anything because you don't expect supernovae to propagate megaparsecs out into the box. But they do have an effect. That's suspicious. And what's even more suspicious, as these effects look very similar to what we saw for AGN feedback. So this probably has something to do with AGN feedback, right? And we can suspect that this strong stellar feedback is probably suppressing the supermassive black hole growth. To check this, we should look at some statistics for the black holes. So on the left here, I have two different lines showing the total number of black holes in the volume. On the right, we have the fraction of the black holes that are in the jet mode. That's the AGN feedback mode that actually affects the forest. Red line is the strongest value for the supernova mass loading parameter. Blue value is the smallest. Dashed lines are the fraction in the jet mode. And on the right, we have Eddington ratios versus redshift. And you can just kind of think of this as what the jet speed is because this is how it's kind of set in Simba. So on the top here, you're going to have lower jet speeds, and below that dashed line, you're going to have maximum jet speeds. So first, we can see when we increase the mass loading parameter, we have less supermassive black holes in the box overall. That is because of the seeding. They aren't able to be seeded anymore because it's suppressing stellar growth. You also have a higher fraction of AGN in the jet mode, which is interesting and would have an opposite effect of having less supermassive black holes, but you have slower jet speeds. But that's only at redshifts higher than about 0.5. So how does this affect it overall? If we look back again at the column density distribution, we can see as we increase the mass loading parameter, that shifts our column density distribution down, removing more neutral hydrogen out of the IGM. So when I say positive feedback here, I mean that it is allowing more jet feedback to happen. So stronger stellar feedback in this case is a positive feedback effect on the AGN feedback in the simulation. But you can see, this is a little bit more complicated than what we saw in the other one. So let's look at the other one real quick. The wind speed. So this is the supernova wind speed. And when we when we look at this, we can see, again, there are less supermassive black holes in the box. They're not being able to be seeded in the simulation. This is a problem with seeding. Maybe we should look at this more. Though you're probably not going to have stellar feedback this strong. So it's just something to consider. You also have fewer AGN in the jet mode. So overall, you should see negative feedback. That's pretty intuitive. And that is what happens. You have more neutral hydrogen in the box when you increase the supernova wind speed because your AGN jet feedback can't really operate the way that it was. So let's visualize this a little bit, just as another pretty GIF that we can all look at and take a break from talking. And we can see, on the left here, we have our low supernova wind speed. On the right, we have our high supernova wind speed. And these little dots are the supermassive black holes in the simulation. And if you look closely, you can see there are much more dots appearing here and over here, and that's really reducing the effect that the jet feedback is having in the simulation. So what are our conclusions from this? Apart from that, AGN jet feedback is pretty important and we should make more models. AGN jet feedback can have a significant impact on the low redshift Lyman alpha forest. We need to look at it more. We need more observation data so that we can constrain it. The faster these jets are, the more dramatic the effect. They can reach out into the IGM and actually cause mayhem. Stellar feedback has an indirect effect because it can suppress the supermassive black hole growth. So this is getting into what we were talking about earlier, like these models can have degenerate effects with each other. They can be intertwined. You need to consider everything. And what I plan to work on next, hopefully, is to build new observationally motivated jet feedback models and explore supermassive black hole seeding to kind of figure out what's going on, figure out how much we need to worry about this. Thank you.
Thank you. Let's thank. Okay. Time for questions. Yes. Okay.
Thank you for a wonderful talk. This is very exciting. So I was wondering, I think you mentioned this already, your black hole mass range. In particular, I'm interested in if you use dwarf galaxies, if you went all the way down to dwarfs.
I'm actually not very familiar with that. I don't know how many dwarfs are in the Simba simulations or how well they might be resolved. I don't know if anybody else would have any insight about dwarfs in the Simba simulations, but I've been mainly looking at the forest and like the black hole feedback model specifically.
Okay, because they might be good candidates. We've seen some AGN in dwarf galaxies, and it's easy to throw out their stuff because they're tiny.
Yeah, thanks for the talk. I think related to that question, if I recall properly, several works have, the effect of feedback, seeing feedback on the black hole growth depends a lot on the dark halo mass and the mass or the mass of the host, because the more massive it is, it's harder. You need stronger winds to prevent the black hole growth. So have you looked at this as a function of mass in the simulation and how this affects?
Like just halo mass?
Yes, the suppression that you see, the effects.
No, that would be probably a very interesting thing to look at, though. I've only looked at these feedback effects as far as the black hole statistics. So it would be more interesting to explore this in the context of the galaxies and the halos in general.
Timing of this is such that you would imprint a correlation between AGN that are in the active phase and the intergalactic medium H1, or is it just a relic that lasts much longer?
To my understanding, the jets kick on in the Simba simulations around Z of 2. So that was one of the things I was going to look at more, is like what the time scale of like these effects actually appearing in the IGM was, how long it takes for them to propagate out. Not something I've looked at yet, definitely on my to-do list. Is that kind of like what you were asking? Okay, I'm sorry. Y'all are asking questions of stuff that I haven't looked at yet. They're good questions though, because I should be looking at this stuff.
Another question on things you haven't looked at yet. Have you looked at different size boxes, resolution?
We have for other studies. We found that for camels, it is largely sufficient. At least up to column densities about 10 to the 15 per centimeters squared, because your sampling is fine up until then. But if you want to past about this line, you're going to have a harder time getting good statistics because you have small halos. But everything below that box size doesn't really affect, at least down to what is in camels, which is the smallest I think we've worked with.
So for all these things, I mean, do you rescale the UV background to reproduce observation, or you just have the one in the?
So we did the scaling to reproduce observations for both the with jets and without jets. But the scaling the UVB for observations is with jets. The fiducial results is the green line, and then the solid green line, and then not scaling the UVB is the black solid line. So they're very similar. Scaling the UVB for Simba. So yeah, that is something we continue. We want to explore that for camels to see which parameter variation would be the best fit with scaling the UVB as well. That's something on our to-do list.
Okay, great. So let's thank Megan again. Our next talk is remote by Festa. It's about building physical model for galaxy sizes using astronomy-driven approach. You can take it away. I will warn you like 2 minutes before.
Okay, thank you. Let me share my screen. Sure. So you're seeing the presenter view?
The presenter view. No, we switch that.
Okay.
You can try sharing that again, and I'll explain how to swap it.
Okay, yeah, that would be good. Yes.
So if you're able to, in the top, use slideshow, you can click on that. That might swap it around for you. Top left-hand side, keep going.
Okay. Yeah. Is it good now?
Now we do not see it.
Anything? Yeah,
let's try resharing that one more time. Are you just using one monitor?
Yeah.
There we go.
Okay.
Great.
Okay. Hi, everyone. My name is Festa Bucinca. I am a graduate student at City University of New York, working with Viviana and Ari. And recently, we've been thinking about whether we can discover a physical model for galaxy sizes using a data-driven approach. So initially, we start with a question whether or not we can discover a physical model for any galaxy property using a data-driven approach. Now, machine learning tools are well equipped to tackle the complexity of such a problem simply because we can learn whether the information is there or not, and which properties mostly contribute to the prediction. And then next, we can use symbolic regression to search for the equation space and learn if there is an equation that relates input and output through mathematical formula. Semi-analytic models are a good setup to test the site pipeline because in SAMs, we know the ground truth. So as a proof of concept, we apply this pipeline to galaxy sizes. Again, semi-analytic models are a good case where we can test our data-driven approach to determine galaxy sizes because the formula that sets galaxy sizes in SAMs is already known. And so we can compare our data-driven derived equation with the ground truth, the correct equation. In our data set, we use the Santa Cruz semi-analytic model, which is a SAM run on TNG 100 dark matter only version of the hydrodynamical simulation. And to make all this more realistic, we try to predict half mass radius, which is something that is usually measured. Now, is the information there? We use two machine learning models as a benchmark to search whether information about sizes is there or not. We employ 31 galaxy and halo properties as features, and we predict size. The first model, the one on the left side, the random forest model, seems pretty promising. We measure the performance of both of the models using the R2 score, where the R2 score is basically a correlation between predicted and true values. So the random forest model performs with an R2 score of 0.92. And so next we use another more sophisticated model like the support vector regressor, where we see a small increment in the performance of the model, as well as a less biased behavior of the predicted sizes in the scatter plot here. So with these two models, machine learning models, we are encouraged that the information is there and that we can move forward to search for the physical model. And so as the next step, we ask what is the minimum amount of features that contribute to the predictions, and if there is such a core set of features that provide a good enough prediction. So in this case, we carry on an add feature ranking analysis, where we start off by looking at the performance of the random forest model when we use only one feature at a time. Then we choose the feature that performs the best, fix that feature, and as a next step, add another feature from the remaining set of features. And we continue like this until we run out of all features. So with this method, we see that there are 6 features that provide a score set of features that are good enough for a prediction. Now, using this set of core features, we search for a physical model. We start by using symbolic regression, a machine learning technique that approximates the relation between input and output through analytical mathematical formula. And the result that symbolic regression gives us is the equation you can see on the screen. This is a promising equation. The variables and the ratios here all make sense physically, and the performance of the model may not be great, but it is very promising. So we expect that there is a difference in the way that disks and ellipticals behave, because that is already known. The physics that governs sizes for disks and ellipticals is different. So we color code the same plot by galaxy morphology, and we see that there is a pattern, that there is a gradient. The red and the yellow dots seem to behave pretty well. And these correspond to disk-like galaxies, whereas the blue and the violet dots corresponding to elliptical galaxies are like outliers. So we are encouraged to now look and search for the physical model by morphology. So now we choose the subset of only pure disk galaxies, which you can see here in the blue color code corresponding to perfectly disk galaxies. We run symbolic regression on pure disk galaxies, and the resulting equation is slightly different. There's a factor of 2 in the v disk over v var equation, and the m disk over m star term disappears. We realized that for some galaxies, the equation predicts smaller sizes, whereas the true size is constant, like the vertical thing in the hockey stick shape here. So we guess that there's a minimum spin value that corresponds to these small galaxies. And when we adjust for that, we come up with a new variable, a spin effective variable, that when using that in the physical model, the performance of the model increases, as you can see in the plot on the right, with an R2 score of 0.96. Finally, we are at a point where we can combine the data-driven derived equation for pure disks with that for all morphologies and come up with a final physical model for all galaxies. The final physical model is shown here, 1.14 m disk m star times spin effective divided by v disk v var square times r halo. The performance of this model is pretty good, as you can see on the plot on the right, with an R2 score of 0.96 on all but elliptical galaxies. You can see that elliptical galaxies are missing in this plot by the color coding here corresponding to disk-like galaxies only. And as the next question, we ask, did we get the right answer? So for that, we want to compare the semi-analytic physical model for sizes with our data-driven derived physical model for sizes. We can see in the two equations here, the one for SAMs and the one for derived by data-driven methods, that both have a spin and our halo term in common. And so we want to compare the factor in front of the spin and our halo term for both the cases. Therefore, we compare the function of spin, f disk, concentration from the semi-analytic model with the factor of 1.14 divided times 1 over v disk v var square from our data-driven derived physical model. I wrote down what this function for semi-analytic models includes so that you can see that it's a long and complicated function. So when I plot the factor in front of spin and our halo for both cases versus the concentration, then it becomes obvious that these two functions do match with each other. The red line here corresponds to the function factor in front of spin and our halo from SAMs, whereas the green dots correspond to the factor in front of spin and our halo from our data-driven derived semi-analytic model. So yes, we think that we did get the right answer. And finally, we will ask whether or not the information for ellipticals is there. So we look at the random forest learning curves for ellipticals, and we see, look at this increasing slope in the green line here from the test set. We see that we need more objects. We need more elliptical galaxies in order to be able to know whether the information for ellipticals is there, whether we can predict elliptical sizes or not. And so as future work, we're thinking of augmenting the population of elliptical galaxies by either adding the TNG 300 box or using some augmentation technique to obtain more elliptical galaxies in our data set. So in summary, we say that yes, we can discover the physical model for galaxy sizes using a data-driven approach using the pipeline I just showed. Thank you for your time, and now I can take questions.
Thank you very much. Questions, Robert?
It's a really fascinating talk. I have two kind of questions, or one and a half. One's a comment, kind of. So, I mean, so how well do you think this approach, I mean, translates to real data, or maybe take a step back to galaxy simulations? Like, I mean, why not try to apply to let's say TNG instead of the SAM based on TNG and see what you would get? So that's my first question. And the second thing is, so have you tried also to distinguish, or maybe what you get if you just look at halo properties? I think that's one interesting question, right? So obviously it would scale with the halo radius, the halo size, but are there other halo properties that maybe also affect this, like the halo spin? Now, if you bring in all the other galaxy properties, of course it might, but the galaxy properties are not that useful if you want to build, let's say, an emulator, right? If you want to say, I have a dark matter simulation and now I want to predict what the galaxy size is. So have you thought along these lines as well?
Yeah, thank you very much for your questions. Yes, I have thought about like all of them. So actually, the aim of all this project is to be able finally to carry on a similar pipeline on the hydrodynamical simulations. But we first wanted to check out as a proof of concept whether the pipeline works on semi-analytic models. And now that we know that this works, our next step is to look at sizes in real setup hydrodynamical simulations. So that's for the first question. For the second question, yes, I've looked a little at just trying to predict using halo properties, but so far I don't have a definite answer for that. I think I have to look more into detail. And I agree that it would be ideal to be able to predict sizes by using only halo properties, but it seems like we need some information from baryonic physics as well in order to come up with a good prediction.
Okay, great. Another question, yeah, Lexi.
Work. I'm wondering, with the symbolic regression, was there one functional form that really stood out with the best R squared, or were there maybe several that had similar R squareds? And how did you kind of pick the best one then?
Yes. So for pure disk, so when I used only very disk galaxies without a bulgy part, it is the equation that I just showed that stood up. The spin divided by v disk v var square times r halo, and that stood up no matter how many times I ran the symbolic regression, no matter how long I tried to search for an equation. So that was what really stood up. I can say the same also when I use the complete galaxies, all the data set, all morphologies. The equation that stood up was the one that I showed. Yes.
So let's thank Festa again for some time. Our last talk is by for this session is by Yu-Heng on big works on big galaxies. So 10 minutes. Thank you.
Okay. Hello. So I want to talk about some observation works about small galaxies. So I said that the title is going to be Small Works on Small Galaxies. I showed my advisor yesterday, and she was like, "This is not small works." So big works on small galaxies. I'm a grad student from University of Minnesota, and most of my works are taking direct spectra of the small galaxies. And by small galaxies, they are stellar mass lower than 10 to the 8. And these galaxies are very faint that you won't be able to have a good constraint on the photometry from the survey, such as SDSS. So what you have to do is either you pick a lot of candidates of the galaxies, and then either you have a deeper survey like DES, or you just have the telescope time to look at each of the candidates, and then many of them will fail. They are just like stars, or they are false detectors. Like when you actually see them, the photometry is different from what the SDSS told you. And so to select a low metallicity or low mass galaxy, what you can do is we have some nearby examples. They are so close to us that they are brighter. And then we take the spectra of them, so get an idea of what the low mass or low metallicity galaxies will look like. And then you kind of get the idea. You can also check with the stellar population models, so that you have like, this is about the range of the low metallicity galaxies. And then you choose the color of each of the photometry, and then goes on to the survey, say, okay, now tell me how many of the galaxy looks like the range of the colors, the photometry that I just told you. And then you will select lots of the objects, which will look like the pictures here. That's blue and compact. So then they also have the name like blue compact dwarf galaxies. And then you point your slit onto the galaxy, take about like half hours or an hour to get the spectra. To measure the metallicity, then you're targeting the aurora lines 034363, and also the oxygen 3 and oxygen 2 lines, so that you can have a direct measurement on the metallicity. And then these galaxies usually are doing a starburst phase. So it's either they have a stronger star formation rate, but then because the size is too small, so the absolute star formation rate is not too high. But then when you look at the normalized, So the specific star formation rate, which is the star formation rate versus the stellar mass, it's 10 to the minus 8, which is considered very high. What's a typical star formation galaxy would have a specific star formation around 10 to the minus 9 or 10 to the minus 9.5. So these galaxies are chosen to be, we can only detect them when they are having the starburst phase, where then they have extra emission lines that's make them brighter. And then for the local volumes or the very nearby, then we are be able to completely study them even when the specific star formation is not too high. So I'm showing the black triangle here, which is the local volume galaxies that's very close to us. And then the rest of most of the studies are when we are studying low mass galaxy, they are doing the starburst phase. And then during the talk, I keep messing around between low mass galaxy and low metallicity galaxy. And that's because there's a mass metallicity relation that the higher the mass, then the higher the metallicity. And when you think about this, it's let's say we have two same metallicity galaxies and we simply merge them together without any more interactions, then the ratio of oxygen and hydrogen would not change. So then what builds up the mass metallicity relation is actually the nuclear synthesis in the galaxy, that you keep changing the hydrogen into heavier element by the star formation. And then this interaction can also consider the interaction, the gas flow between the circumgalactic median and the ISM itself. And so next up is that for those low mass galaxy, you have a relation. You see most of the galaxy have the relation of mass and star formation rate, and where we are targeting the highest star formation galaxies at low mass end, because that's the only way we see them in observation. And then there's also, for most of the galaxy, and including the low mass galaxy, there are mass and metallicity relation. So then people can think of, okay, now if there is a common trend or common relation in mass and metallicity and star formation, can we combine them all together? So then people start to looking at a relation between mass, metallicity, and star formation, which they call it fundamental metallicity relation, that all the star forming galaxy sequence falls onto a 3D plane between mass and metal and star formation rate. And specifically, you'll see that at the same mass range, the higher star formation rate is, then the lower metallicity it is. This is not a causality to say that star formation cause low metallicity or low metallicity cause star formation rate. It's simply just a relation we saw. And this relation has been studied for high mass galaxies. By high mass, it's like above 10 to the 9. It's quite clear that there is a plane, but then below 10 to the 8, it has never been studied very well before. And then for my sample, which is about 70 low mass galaxy, none of them are really falling on this mass metallicity star formation plane. Now, how does the plane form for the higher mass galaxies? Lots of theory have been proposing how you can regulate the gas and the star formation all together, so that you can have outflow that blows away the metal, and then you have inflow that brings in the pure pristine gas that's only hydrogen and helium. And then inside the ISM, this is the fuel, your budget to form stars, and then back and forth, back and forth. Now you can see that this model is also depending on the environment of the low mass galaxy and also the halo mass and so on and so forth. And this all together, if you are reaching to some stable states or equilibrium state, then you can have a regulated relation on mass metallicity and star formation. And since we only recently have the chance to, by reasons like maybe recent 5 years, we only start to look at the low mass end of the galaxy. So it is not clear whether a low mass end also have this relation of star formation rate and metal and mass. And in fact, it's even not clear whether like this stable regulation between gas flow and star formation works for the low mass end. So that's one of the things that in this workshop I would like to have collaboration with is that from observation side, it's very challenging to actually target the low mass end. And our job is just to keep going on and on with like JWST and HST and other surveys to target the low mass galaxy and provide more and more data. But then it's very hard to study the galaxy itself is already hard, and then it's almost impossible to study the CGM of the low mass galaxy because they don't have emission lines, they don't have too much continuum. So then this is a field where the simulations can bring lots of insights of what's going on in the gas flow around the low mass galaxy. And then observationally, there are some approach to study the CGM. And one of the way I'm showing here is like, this is the HST filters of F150 nanometer and 165. So if you have the target that the F50, the Lyman alpha redshift into the F50, then you can simply, you can kind of having one filter that only capture the lights of the continuum, and then the other captures the continuum and emission. Subtract the two, then you'll get the emission line of Lyman alpha, which traces a neutral gas of the CGM. And that technique also need to be considered that how far the galaxy you are against the Earth, so that your aperture, not just the image, but also the spectra that you take can cover the entire CGM, so that you can have a cross study between image and the spectra. And that is quite rare of the opportunity that you can have HST images and spectra at the same time. And then once you have those kind of things, and then you can study the scaling relations of the CGM, and then looking at their scales compared with, say, high redshift, where the Lyman alpha is in the opticals. And then you can study like whether the Lyman alpha or the light curve of the Lyman alpha agrees with the high redshift versus the low redshift. And by far, it doesn't agree. And then there are a couple of more ways to study CGMs, such as if you happen to be lucky that there's a dwarf galaxy where within the virial radius, there's a background quasar that provides a UV background. Then once the light goes through the CGM, it'll produce some absorption lines on several metals. And then you can use the absorption line of metal to calculate the column density. So it's a summary of the CGM at that line site. And then you collect lots of the dwarf galaxy with the background. So then you kind of get idea of what's going on along the CGM, that assuming that all the dwarf galaxy have a similar profile of the column density. And that's like another way to do it is exogenously, if you have a very high resolution spectra, then you can model the influent alpha of the gas to see what is the best match of the line profile that creates what is the best condition to create the line profile. So that is what I have to say about the low mass galaxies. And then last part, I don't have a summary slide, but the last part is that these low mass galaxies, how much are they alike to the high redshift galaxy that we've seen in JWST? And I have to say that for JWST, there's some selection bias probably that we also tend to see the most starburst high redshift galaxy, because these galaxies can have a low specific star formation rate, but then when that happens, we simply won't be able to detect them. So that's I'm going to conclude that these low mass galaxies are very hard to study, but then that they are the object that I think are most similar to the high redshift galaxies. And then I would like to have more collaborations with observations on the low mass galaxies. Thank you.
Oh, yes, time for maybe one or two quick questions.
Hello.
Yeah.
Thanks a lot for this wonderful talk. I had a question about, you were talking about how they might fit on the fundamental mass metallicity relation. And I guess part of the question is, whether they follow the gas regulator model that you described. But I guess my question to you then is, do you expect them to actually be in an equilibrium state, or are they actually already, excursions due to the fact that they might be very young starbursts and only just now forming, not yet had time to enrich their ISM or do anything else in a way that's observable?
So one thing that I make the assumption is that, so for a high mass end, there is a kind of relation that's quite tight on the fundamental metallicity relation. And there are galaxy groups that's similar to these, that they are low mass, but they are similar to the main sequence star-forming galaxies. And say for the local volume legacy, they have a similar specific star formation rate. But then even these galaxies do not really fall on the metallicity plane, the 3D plane. So that's one of the things that's like, I'm assuming that having the similar sequence there, like if you take the local volume legacy as the extension of this star formation sequence, they still don't follow the plan. Then if that's the case, that I would say there's probably different regulation between the three quantities, or that, you know, just because it's so low mass that this relation doesn't exist. Yeah.
Great, thanks.
Just one quick question.
Hawk, is it clear what's, in any of these cases, what's driving the starburst? Is it a merger potentially? I mean, some of the images look like there could be potentially, yeah, like this top left one. I mean, is anything known about what's driving the starburst?
So in the observation of, like, I observed maybe 60-ish of the galaxies, the case of that have merger signs are quite rare, because I would say if there was a merger sign, then the morphology of the galaxy should be more extent. And most of my galaxies are very compact that it's not resolved. So it's not necessarily the merger that caused the starburst. And my understanding might be very biased from the simulation, but my understanding of the starburst usually is that when you have enough gas from the halo, accrete from the inside the halo, you simply would have the environment to do the starburst.
That gas has to come from somewhere. So yeah, I think interesting.
So yeah,
we can talk more about it.
Okay, okay.
Yeah, we've done some simulation studies of this.
Okay.
Let's thank you, Heng, and all the speakers for this session.